In this lecture, we are going to derive a relation for turning moment or torque applied on the shaft. Right? In previous lecture, we had considered arc BB dash on the cross section of the shaft. To know, so this is our shaft, right? This is the centroidal axis. Now here consider a small elemental area D and turning force acting on this area is dF. This force dF is responsible for the turning of shaft about the axis of rotation, right? In this direction, clear? This direction. So if distance is r, then turning moment will be T equal to, for this elemental area, if turning moment is dt, then dt will be equal to df into r. If we make a cross-sectional view for this elemental area, which is at the portion of BB dash discussed in previous section, I am making the circular cross section, right? This is the large view of this cross section, right? Now consider a small elemental area, a small elemental ring, right, which is a distance r from the center, and total distance is capital R, right, from the center, the outer periphery of the shaft, and the thickness of this ring is dr. Thickness of this ring is dr, right? Then this force then turning moment developed at this elemental ring is df into r, right? Now df, if shear stress at this section is tau dash, then this will be, df will be equal to tau dash into dA into r, right? Area of elemental ring will be equal to tau dash, area of elemental ring will be 2 pi r dr into r, length into thickness, right, will be the area of elemental ring. Clear? Now in previous section for BB dash we have made a relation that for a fiber of shaft, right, at a distance r, if shear stress developed is tau dash, then tau dash by r equal to tau max by r, because capital R, because tau upon r bears a constant ratio. So it will be equal to, in previous section we have discussed that tau dash by r will be equal to tau max upon capital R, where tau max is the shear stress value for the outer periphery of the shaft, right, and r is the radius of shaft. But here elemental radius for elemental ring is r and shear stress developed at the ring is tau dash. So therefore here tau dash can be replaced by tau max by this equation, tau max into small r upon capital R into 2 pi R dr into R. Right? Now this whole expression can be done if we apply integration. If we have to calculate the entire turning moment, torque developed on the shaft, then integrate this whole term for the value of radius which will vary from 0 to capital R. Right? dr vary from 0 to capital R. dr here, dr vary from 0 to capital R. Right? So dt will be 2 pi tau max upon capital R is constant, so make it out of integration symbol, and here will be R cube into dr, and dr is varying from 0 to capital R. Right? Now this dt is now will be equal to T. This is the total torque applied on total turning moment applied on the shaft. Right? And here when we integrate it, then value will be 2 pi tau max upon R into R to the power 4 upon 4. This will be very 402 R. Replace this whole term, then it will be R to capital R to the power 4 by 4. 1 power will be cut from this R, then value will be 2 pi tau max into capital R cube upon 4. Now if you put the value of R in terms of diameter, in terms of diameter of the shaft, right, R equal to D by 2, then it will be reduced to pi by 16 tau max into D cube. This is the required expression for the turning moment, right, of solid shaft. Clear? Pi by 16 tau max into D cube. Now here this whole term pi by 16 tau max T cube, say this is equation number 4, because in previous lecture tau by R equal to G theta by L was the equation number 1. Clear? Now this whole expression, this equation can be written in the form of T upon pi by 16 into D cube equal to tau max. Clear? If we multiply divide d by 2 on both sides, we divide by d by 2, then this expression will be reduced to T upon pi by 16 into D cube into D by 2 equal to tau max upon D by 2, or it can be written as T upon pi by 32 D to the power 4 equal to tau max upon r. And this term is replaced by, we know, already we have studied in centroid and MOI portion, that T upon IP. This one is equal to polar moment of inertia of circular cross section, right? Yeah, moment of inertia of circular cross section about its polar axis, right? T upon IP equal to tau max upon r, right? This is the equation number 5. Now, already we have made an expression that tau max by r is equal to g theta by L. In previous discussion, c theta by L, in previous lecture we have mentioned it. Then this equation can be rewritten in the form of T upon IP equal to tau max upon r, and this will be c into theta upon L. This equation is known as torsion equation for the shaft. Torsion equation of the shaft, right? There are some more definitions coming out of this expression, that if the torque, like definition of torsional stiffness, sometimes numerical problem, values are given in terms of torsional stiffness. Then what is torsional stiffness? Torsional stiffness is basically the rearrangement of this torsion equation. It is denoted by the parameter torsional stiffness equal to T by theta. It is also defined as torque per unit angle of test. Torque per unit angle of test. To make it right, this is T by theta. This will be equal to, if we take this one and this one, then T by theta will be equal to C IP upon L. Right? This is the turning moment or torque per unit angle of twist is known as torsional stiffness. Right? There is another parameter, torsional rigidity. Torsional rigidity. What is torsional rigidity? Torsional rigidity, it is defined as the torque per unit angle of twist for unit length is known as torsional rigidity, right? This is, I think I should write the definition. There is a very minor difference between torsional stiffness and torsional rigidity. Torsional is value of torque per unit angle of twist is torsional stiffness, and torsional stiffness for unit length is known as torsional rigidity, right? That is equal to, you can write it, torsional stiffness for unit length, right? This expression will be represented by T by theta into L, right? Here L will be 1, again this equal to T by theta. For unit length, this will be equal to C into IB, right? C into IB. Here, for torsional stiffness, right, the unit will be Newton meter per degree radian, right? Per radian, yeah, per degree angle. And for this one, unit will be, right, Newton, this is IB, unit will be mm to the power 4, and here this will be Newton per mm square. This will be equal to Newton meter square, right? For this one, unit will be Newton meter square. This is torsional rigidity, and there is another term, right? This term is known as torsional strength. This is very important one. What is torsional strength? We will discuss it. Torsional strength, right? It is also known as polar modulus. What we call it? Polar modulus. It is denoted by a ZP. Right? This is denoted by ZP. ZP is defined as the ratio of polar moment of inertia to the radius of shaft. ZP is equal to IP upon R, right? For circular section, because in the syllabus there is circular section of the shaft, then IP will be equal to pi by 32 d to the power 4, and R will be equal to d by 2, so it can be equal to pi by 16 d cube. So ZP is equal to pi by 16 d cube. Clear? Now here, from equation 4, when we derive a relation between T and tau max, right? Then T equal to pi by 16 tau max d cube is the expression. Here, for this term pi by 16 and d cube, we can write the equation, right? We can write the equation T equal to, we know that T equal to pi by 16 from previous discussion, tau max into d cube, or pi by 16 into d cube is equal to tau max into ZP. This is T, right? This is our ZP. Here, if shear stress tau max, value of tau max is unit, if you consider the value of tau max unit, right, then T will be equal to ZP. So we can say that torque per unit maximum shear stress is known as torsional strength, right? Torque ZP can be defined as, if value of tau max is unit, if we consider tau max as unit, then torque per unit, torque per unit of shear stress is known as, this is always should be maximum, right? Because ZP is always dealing with radius R, and at radius R tau is maximum. So torque per unit of maximum shear stress is known as torsional strength. So T will be equal to Zp, or Zp will be equal to T when tau max is unit. Right? So this is all about the turning moment or torque applied on the shaft.